Moving on with the review, the component level review of my motor controller board. So this is my motor controller board. You can see the detailed design process for this board in my other videos. Right now I'm doing the component level review. So I'm going through every single component and I'm checking if that component makes sense to be placed where it's placed, whether it has the right voltage ratings, and whether there is anything missing around that component. So today, in this video, we're going to be looking at the diodes. I have exported all of the components from the schematic using a simple Python script, which produces this CSV file, through which I can just go line by line, and I have the component manufacturer number, and I have the package here, so I can double check that it's the right package, and I have a link to the datasheet. So let's get started. We'll start with D1. D1 is here. So the purpose of this diode, this double diode, is to protect this input of the op-amp from going beyond 5 volts. So what will happen is when the signal here exceeds 5 volts, a small current will flow through this connection here and into the 5 volt supply. Now, because the current is small, it's not going to increase the voltage on the 5 volt rail, and in fact the regulator that's running there is going to do its best to regulate the voltage so that it's stable. But having a resistor is very important here, because this resistor limits the amount of current that flows here. So any current that flows will get consumed by all the components that are connected to the 5 volt rail. Actually, in this case, it's only a few components that are connected to this specific rail of analog input VDD. But it's still going to sort of anything that goes out there is going to be very small current, which will not be an issue for any chips that are connected to the 5 volt rail here. But the net result is that we're not going to ever exceed 5 volt plus some small voltage, which is the voltage drop for this BAT54 diode. I think it's around 200 millivolts, or slightly smaller than that. So very good to have this configuration on every single pin that is connected outside, where the signal can be, for whatever reason, can be higher than what was intended. So this pin on the op-amp can tolerate up to 7 volts. So if we limit this to 5.2 volts, then we're fine. So we can say, let's double check the footprint of this BAT54 diode, just to make sure that we have the correct footprint. So I'll go to the data sheet of this diode. Let me pick up the data sheet here. I'm gonna open it up and then I'll just check if this pinout is correct, because there are several BAT54 diodes where you can have different configurations. I wonder if this one is, in fact, this one is SL. Is this the right? Is this the correct configuration? Let's check. SLT1G. So this seems to be the data sheet specifically for this variation of the BAT54S diode. The package is SOT23 and not SOT23R. There's different variations of SOT23, and the difference between the different SOT23 packages is that the pins can be numbered differently. Here we see, let's see, is there any pin numbers here, just to make sure that we have the right footprint? 1, 2, 3, right. So we have 1, 2, 3, and we have 1, 2, 3. So it's 1, 2, 3. Basically this thing upside down. 1 is the anode. Let's double check that. 1 is a node, 2 is the cathode, and 3 is the midpoint. And it seems to be exactly correct. And looking at the footprint for this diode, let's see, SOT23. Biggest problem with this footprint viewer is that when I click pick footprint, it should actually choose the chosen footprint. Okay, so this is, where is SOT23? Wait, so what was the, oh, okay, package TOSOT SMD. So we can look at the generic one. Package TOSOT SMD. SOT23. Could it be? Let's see. SOT23. There we go. It's 1, 2, 3. Yeah. 1, 2, 3. 1, 2, 3. 1, 2, 3. I'm pretty sure this is the standard SOT23. And that looks good. So we can at least be sure that the package on this diode is correct. We can green light this one, and then I will also green light all of the, let's see, let's close this one. I'll also green light all of the diodes that come underneath it. So 1, 2, 3, let's see, 4, 5, and 6 and 7 and 8. Yeah. So all of them. 1, 2, 3, 4, 5, 6, 7, 8. These are green. So next one, D10. Let's see. D10. The sorting is all screwed up because I just sorted it by as strings. So I didn't bother to parse the references and then sort them by numbers. I just sorted them by strings. So you end up with this kind of situation where you get D1, then D10. Okay, so D10 is an ESD protection diode for the CAN bus. And when you see those ESD protection diodes that are back-to-back diodes, that means that the way this diode is going to work is by limiting the swing on each line to plus minus the rated voltage. So whatever is the rated voltage on this diode, we can check that. Let's see. It's probably something like 30 or 40 volts. That would be the limit above which the diode will conduct to ground. So anything above that limit will go to ground. So diodes, they work like dams. So you can have like where the dam is built such that there is a certain level where the water starts to overflow the dam, and the water level cannot rise past that level because anything that comes past that level will just overflow and flow downwards, downstream, and anything. But anything that is already downstream cannot flow upwards because that would be kind of trying to push current in reverse direction. Some diodes have this breakdown voltage though, that in reverse direction they will break down at a certain level, and then they start to conduct, and that's what happens in this situation here. So you have two TVS diodes which start conducting when the voltage is either plus or minus a certain certain level. So we can see here. Let's go to let's go to the data sheet of this diode. I hope that was a clear enough explanation. I could do a video on just the diodes, and we can do some simulations on that later. But for now, I'm just going to be focusing on the review. So let's see. We have ESD CAN, which one? 06. So 06, we can see breakdown voltage is 38 volts, right? Now, it's important to match that with the maximum voltage that this chip can support. So TGA 1044, we have to go to the datasheet of TGA 1044. And we have to check the absolute maximum ratings of the input pins. Plus 42 volts, plus minus 42 volts. That's the maximum voltages that this chip can handle on the input pins. So let's see, where did I have that data sheet? Yeah, cancel. Yeah. So typically it will start breaking down at 38 volts, and then it will sort of gradually, or in this case probably fairly quickly, just cap the voltage at slightly over 38 volts, depending on the device. There's usually like a small bit of room there, but we can use the 38 volts diode, and this will work fine, but I need to just double check the pinout. So 1, 2, 3. This looks like a standard SOT23, but I have to make sure. So let's see. We have 1, 2, 3. Yeah. 1, 2, 3. 3 is the middle. 3 goes to ground. That's fine. And the footprint is actually SOT323. Is this SOT323? Yeah, 3L. Okay. So it's 323 SC70. Yeah. Okay. SC70. 1, 2, 3. Yeah. Cool. That's correct. Okay. And anything else we need to, let's see. Okay, so this is the minimum voltage when there is a pulse of minus 150 volts. So you get 44 volts. So that's actually higher. I think we should use something. I think actually with this transmitter we should use something different. We should actually keep this to probably use ESD CAN 03. This seems to be a much better choice. I mean, otherwise there wouldn't be any point with having such protection if the protection lets through voltages that are higher than the chip can handle. So I want to fix this. I don't want to use a diode that is not the correct one. Or actually, could this be, let's double check this. am I understanding this correctly? So maybe VCL is actually the locking, the clamping, okay, clamping voltage. Okay. Right, so it's designed for 24 volts. It starts to break down at 26 volts, and the maximum pulse voltage would be minus 34 volts. Well, this actually makes sense because we have a use case for 24 volt system. But let me think a little bit. I think I'll go with this one if, let's see, this one, yeah, this one is available. So I'll just change this to, let's see, okay, that is DCAN 06 there. Okay. I'm gonna go with the 03 for this design. I used 06 before. So the question is like, what happens if power line is connected directly to the CAN bus, like if there is a short? And that's what is likely to happen sometime. So make sure that this diode can clamp the voltage to below the level that would be destructive to the CAN transceiver. Yeah, let's go with this. So this would be ESD CAN 03. And actually I can go CAN 06. Can we find it? Yeah. Let's see. Okay. ESD CAN 03. And I think there's another one. Yeah, that one is ready. Another one. Okay. Let's see. Is it this one? Yeah, it's this one. Yeah, that was the only one. So since I'm using the same transceiver, I can just use the same ESD diodes on each transceiver. So I'm gonna green light those. This should be fine. And the third one is DCAN there, D13. Okay, so moving on to the next one. CDVC D12. What does D12 do? D12 is a switching diode for this regulator, and this one is chosen based on the current rating of this regulator. It's 3.5 amps, and the diode is chosen to be 5 amps. The only thing I want to check about this diode is, let's see, I want to check the footprint. Let's see, it's SMC, and I'm gonna double check that it's really SMC. And I also want to check the footprint just to make sure. Okay, here we go. So it's DO214AB2. Let's see what that actually means. DO214AB. Yeah, an AB2 just means it's 2 leads. And that's basically SMC. Let's see. Let me check the properties. Okay. I probably don't need to check the pin out, but I'm gonna do it anyway. So it's pin 1 is cathode. Then if we open up the footprint for SMC, pin 1 is cathode. Great. Okay, can green light that one. Let's see, and green light that one. And next on the list is SMPJ12A. It's D14, and it's right here. So this is a TVS diode for rated at 12 volts. So it will start conducting when the voltage is slightly above 12 volts. This one is designed to control the voltage on this rail. So if for any reason this rail goes above 12 volts, then this diode will start conducting. And the smart thing to do here would be to place a fuse somewhere here. So let's go ahead and do that. So what will happen is, if the voltage goes above, now the thing is, so it's going to depend on where from this voltage is coming. So if essentially we want to actually place the fuse here, or no, can't, because that would be stupid. But if I place the fuse here, that would be kind of, the fuse will burn down if this regulator for some reason provides more than 3.5 amps. But that's not necessary, because this regulator is has overcurrent protection. So what will happen if you just short this line here is just that the voltage will drop. The other situation that can happen is that something is connected here that pushes more than 12 volts into this circuit, in which case probably this resistor will burn down if there is significant current flowing through here and down here. Now this regulator can go up to, I think, 17 volts. So there is a certain margin there where basically you can have a voltage that is higher than 12 volts here, and it's going to work just fine. So the question is whether we actually need any fuse here. and I think that that will be just highly unnecessary in this case, because the fuse will just never burn down if it's placed here. And if it's placed here, it's going to burn down, but the question is how useful this would be to have any kind of fuse here. Whether this connector doesn't really have a use case besides being an output for connecting 12 volts. So maybe what we could do is we could place a 3.5 amps or like a 3 amp fuse here, so that if something gets connected here that causes this diode to short, then the fuse will go. And if something is connected here that takes over 3 amps of current, then the fuse will go as well, which is good, which is desirable. So I think putting a fuse here is actually a very good decision. So let's have a look what fuses we have. I'm gonna search for fuse 3A. And we have 0402 fast acting fuse. Let's see. I want to find something that's in stock, and I want to just pick fuses. So 3 amps, that's what gonna let's see, and DC, let's make it 12 volts. Or actually, that was a stupid decision. We want something that is 12 and above. Let's make this 12 and above. Then we get 400 to choose from, which is much better than 2. And what else do we have? Okay, so I'm going to sort this by price, and I'll pick something that is small and preferably surface mounted. 3 amps, and what is the package? It doesn't say what the package is because I have to surface mount. Yeah, I have to pick surface mount. Oh, actually, that's interesting. Surface mount with fuse holder. That's very interesting. This is great, but they're so expensive. That's so expensive for a fuse. €2 for a fucking fuse. Okay. 5,000. So these are a few that can be chosen. So on the one hand, it's easy to replace a fuse like this. On the other hand, it's a little bit expensive for a fuse. Like, I'm sure of course we have to have a fuse there, but what type of fuse, I guess, I want to pick something that is a bit cheaper. 1206. Although, now that I think about it, I think it's probably better to just pick this fuse with a holder, because that just makes things so much simpler. Let's see. Surface mount fuse with fuse holder. Let's see. Let's go with this one. Little fuse. Yeah. Oh, this is good. Okay. Time to add a fuse. Let's see. I think that I have a few inductors here. What is this? Yeah, we can use this one as basis for the fuse. Fuse 3 amp. $97.50, I suppose. No, that's fine. Wait, what's this one? And we can do then is add a line that goes just straight through that. Really? Did that not work? Okay, that's great. I'm gonna delete this one. Yeah. So, and this would be F as a designator, and as footprint, I need to choose. I need to make a footprint for this one actually. So let's see. Fuse. Are there any fuses here in the default footprints? Maybe CB fuse. Fuse holder. Little fuse. So that will be 97.50. So it's 10 millimeters. This could be a. Let's see. Yeah, this could actually work. This one. But I have to edit it and just see 29. Let's see what this footprint looks like. Unfortunately, I have to close this and I have to start the footprint editor to see the exact dimensions of this footprint. So I'm gonna go to fuses and open this one. So let's measure this. It's 872, so we would need to make it bigger, and in terms of width it's 550, whereas in this case it should be, yeah, let's just redo this. So 424, 381. Interesting. Okay. So this was wrong. It's actually 424, 381, like that, and then the same thing here. 424, 381. And the distance is 213, so we can do like this. Press space, and then I move it 213. That will do. And then I'll just move this whole thing a bit here. Okay. So just making sure that position X minus 322 and position Y X minus, okay, maybe minus 3.2, that's what we can do. And this one, yeah, 3.2 and minus 3.2. Okay, so this would be 216, 212, yeah. Pretty much similar to this, and 1062 on the full length here. So, yeah, this is the right size. And then I'll move this thing here. And I'll just increase the size of this. Let's make this whatever. Just holding Control key to make it straight. Yeah. And then moving this one out as well. So the component itself is 973 long. So if we make this start point minus 4.6. No, let's see, 9.73. So that's around 4.5 4.85, something like that. Yeah. Yeah, this is better. And this one as well. Okay, this is taking too much time now for the sake of a fuse. But as usual, when I see something that I think needs fixing, I want to fix it right away instead of waiting until I get to this fuse later. So let's see. This one can go there. Okay, now this is a little bit off. Yeah, that's better. So we got -6 start point X, and 6 would be here, and then we can make this one the same size from 6 to -6, and then the last few details are these corners here, like that. Okay, looking good. That's the fuse, and this is going to go into custom, and this would be package. Yeah, that's packaging for the, yeah. Let's see. Let's call this little fuse. Could we call this 9750? Yeah. Okay. And then in the part editor, I'll change the footprint of this fuse to the little fuse footprint that I've just created. There we go. Awesome. I'm gonna save this, and I'm gonna run my script that updates the library. Okay, so now I can move this out, and I can stick the fuse in between here. I think that I can even do like this, and if I just add the fuse here, fuse, yeah, this one, rotate, place it there. There we go. So if the current for some reason through this connector gets over 3 amps, actually I'm gonna do like this. I'm gonna write text here, 3 amps. Yeah. So if the current goes above 3 amps, then this fuse will go, and one of the ways that this can happen is if the voltage is too high, so that this diode shorts, and let's see actually what this diode can take. So D14, it may not actually be able to take 3 amps, so we have to check. I'm gonna check the data sheet of this diode. peak power. This is if you have really high voltages. But is there any kind of peak pulse power? So I suppose that would be kind of, okay, here we go. Okay, right. SBJ 12. It's like 31 amps for a short pulse. Okay, so they're pretty durable. They can handle high currents. And in the datasheet for the fuse, how long time does it take for the fuse to burn down? Let's see. Doesn't actually say how fast. Nope, doesn't say how fast the fuse will burn, but it says fast acting, so I assume that this is okay, very fast acting and time-lag options available. Okay. Yeah, and the holder can fit several fuses, several types of fuses. Okay. So yeah, if the voltage goes beyond 12 volts, then eventually this fuse will burn down. And that's for, and also if the current drawn by anything connected here goes above 3 amps. Great. So moving on, what's next? Next is D15, SOD 323, and the diode itself is one of these. Let's find this diode. SOD 323F2, SOD 323F, with 2 pins, and where does it go? D15. Okay, so this is kind of like a, let's check what type of, it's a Zener diode, right, 3.3 volts. This is just sort of to regulate any kind of voltage spikes here. And it's not strictly necessary to have this diode here, but I still use Zeners on the 3.3 lines when, especially because in this case it's there is nothing that will feed any current into this 3v3 line, except for possibly something that's connected here. But then if the voltage is higher than 5 volts, then this diode will conduct and feed it into the 5 volt rail. So it's really kind of like, yeah, this Zener can actually burn down if the voltage goes above 3.3 volts here. So we should probably either use a 5 volt Zener in this case, or we should not use any Zener at all here. Yeah. Let's see what the other diode of the same type does. So now we have D16. D16 is on the MCU. Yeah, so there is nothing to limit the current through this Zener. So I'm thinking that maybe this, using these Zeners, is actually not. Yeah, they should at least be. They should at least be able to tolerate 500 milliamps, which in this case they can't, because the power rating is way too small. So I'm gonna search for Zeners that are of higher power. Something like 1.5 watts or something in that range. So we got some Zeners here which are pretty powerful, or rather have a high rating in terms of power. Oh, there's so many different packages that they come in. It's incredible. So 200 milliwatts, 0.200 watts. Let's see. Maybe maybe I can pick something that is between 1 and 3 watts. Let's see what we get here. Yeah, this one looks much better. 3 watts and let's see, SMB package. Let's see, 3 point. That SMD, and it's going to be an SMB. Okay, and I'll just remove that. So let's change this to yeah, and then the diode that we have here, I'll just remove that one because that's completely unnecessary. Yeah, this one can go. Okay. I'm gonna run my script that updates all the fields. And I'll update the field values, and I'll annotate the schematic. Okay. So now we have D16 and D15 is gone. So I can green light both D15 and D16, those are fixed. D17, 18, 19, that's more protection diodes. This one will protect the VMOT sensing. Oh, there's another one. Right, okay. Okay. So actually in this case, it's good to have the milliwatt Zener because we don't have any high currents coming here. So I think I'll keep this one actually. D33. So D33 is actually not in here. Right. I got that added afterwards. So okay. Yeah, I'm going to keep this. Yeah, I'm gonna keep that as the 200 milliwatt Zener. And D17 is fine. D18 is there. So the only purpose of D18 here is to allow connecting the VCC here when in-circuit programming this EEPROM. So I have a diode here that stops this voltage from going to the rest of the circuitry. And I'm a little bit unsure about this EEPROM, whether I would have to like in-circuit program it. It would be best if I could program it over LAN or perhaps over SPI, but that could be impossible. That's something that I need to research a bit more. So D18 there. I was just looking for that designator, but it ended up there, so I couldn't see it. There we go. So D18 is green, and then D19 is, what do we have here? So this one is also too high up. The D19 and D21 and D25. These are designed to protect the voltage sensing from each phase. So actually, since I'm not using any Zeners here anyway, and since the currents are so small, I think I could safely actually remove this Zener that was here somewhere. Let's see, where was it? I think it was here. I can just remove this Zener, and I think it will be just as safe, because it won't really matter. If this voltage spikes, then most probably the voltage on the phases will spike as well. So let's continue with this review here. Let's see, where is it? So this was here. Right. So we got D19, D21, D25, and then D20. D26. Six diodes. And then we have D23. Where's D23? Okay. The D23 is a protection diode which has 3 elements inside it. So it's kind of like the BAT54 that I've been using, but I have 3 elements in one single diode. So this is better, and then this protects the HAL inputs from any over voltage that may come on the inputs here. Usually though it will be 5 volts coming in here, so it will be just divided by it will be roughly 2.5 volts, or let's see here actually. No, it will be around 3.3 volts actually here. And anything that goes above 3.3 volts will be automatically protected here. So what can happen is that any one of these resistors can get bad solder joint, and if that happens, then there will be 5 volts here, which is important to make sure that we protect against. So D23 and D24. And D27 is a BAT54. D27 I have already. Didn't I already accept about 54 somewhere? Interesting. What diode was that? Okay, this one is definitely okay. D28. We got the D28. That's the diode that feeds all of the circuitry, the logic circuitry, and the purpose of this diode is to stop this capacitor from discharging over the power rail. Because if it can discharge over the power rail, it can discharge very quickly, and then there's no point in having this capacitor. But what we want to do here is we want to, since we have a power rail that can fluctuate a lot, especially if we have an overcurrent condition, or if we are engaging the brake, then this power rail can actually go to 0 volts. So we want to make sure that for those small moments when the power rail fluctuates a lot, that we have some storage here to run the logic from. So that's why I put this 100 volts 5 amps diode here. Now just to double check, I think let's see, CDBC 520, CDBC 510, yeah, 5100. That's an SMC diode, yes, SMC there, okay. So this one is green, and just, we'll just go here and make it green. And then there is this D29. D29, what does D29 do? Okay, so the purpose of D29 here is to is actually to supply the motor power and to keep the voltage from the motor from coming back into the supply. So we have the, let's go back to this circuit here. So we have the brake going from here to here, this label, and then this goes into VMOT through this diode. And as the voltage rises on VMOT, then we get a situation where this transistor will open. I've actually simulated this circuit, and I think it's available in a different video. But what will happen here is that when VMOT rises, this circuit will engage the brake resistor, so that the voltage on VMOT can drop through the brake resistor. And now let's see here. Yeah, so VMOT is also coming in here. And so VMOT is going to be shorted over the brake resistor to ground through this MOSFET here. And so by doing so, we'll be expanding this energy that comes from the motor through the brake resistor. Now, it could be useful if we want to use regeneration to actually short this diode and have VMOT connected directly to this brake or to this input. But this can be done. By simply connecting a wire from this pin number 1 on the brake input to the VCC here. And if we do that, then we're effectively shorting this diode here, and anything that comes from VMOT will flow directly back into the supply. So D29 is quite useful, and it's a high power diode, so it's capable, I think, of 100 amps or something. We can double check this and make sure that we have, so let's see, and it's SOT 263. Let me go to this window here. So let's make sure that it's correct pin out. So 132. And actually the SOT 263 is the same as D-pack or D2 pack. Let me check this. If I go to this footprint. SOT263. Or TO263. Yeah. TO263. And we have A1, A2, anode, cathode. So anode, cathode. Cathode is 2. Anodes are 1 and 3. So yeah, anode is 1 and 3. So this is correct. Let's go back to the list and mark this as green. And then we have D30. D30 is a diode that's connected here. The purpose of this diode, I think, is to let's see. What was this used for? This is an interesting situation here. Let's see. Can I perhaps open? Let me check something. I'm gonna open this. Let's see. I'm gonna try to find this circuit that let's see, brake resistor. Let's have a look at this one. So we have BAT 46 here, and it's 10K, 10K. Well, I have 135K, 135K. So what is this? Why did I simulate it with 10K? But then I used 135K. That's weird. So let's see here. So this one is limited to 49 volts, which is intended, right? The current flows up to 1 amp through this resistor here, which would be the brake resistor in this case. And the current here also is probably something similar to that. Yeah. Now, what is happening here? So the current through this diode is like microamps. Essentially, what if we remove this diode? I have no idea why I put the diode there. Okay. And what about this? Yeah. So this goes to 35, 49, 35. And if we delete this one, is there any difference at all? Yeah, 35, 49. So this doesn't seem to be any different. Yeah. And but why 135K. Yeah. That's like microamps. Right, so 135K was probably, I don't know. Yeah, I have no idea. Why 135K? I think we should actually replace this with 10K. Let's see. Because this is absolutely unreasonable. What is this? Why? Yeah, I have no idea. I don't know. This should work without any diode and with 10K resistors. So if I make this 10K, I'm just going to check what the currents will be. 10K. So the current through this resistor is like microamps. Yeah. This one goes roughly to 3 volts, and then we have current through the brake resistor as it triggers. Yeah, this should work fine. And we got 10K there. Yeah, cool. Okay, so I'm gonna green light at least. Yeah, I'm gonna green light that one because I fixed that. And D31 is a LED. Let's see. D31 is a LED connected over 470R resistor. So this is 603 and the LED itself is, let's see, I'm gonna open the footprint and just, I'm gonna check the, let's see, so one is, I suppose one would be cathode and two would be anode. And so I have to edit this with the library editor to see the pin numbers. One is cathode and two is anode. Okay, seems legit, and it's a 603 diode. Okay, so this is green as well, and the last one is SMBJ48, which is directly at the input. D9. And the purpose of this diode is to catch any voltages that go beyond 48 volts. And actually, there should be a fuse here, which we'll see here. I'm gonna check how many amps this diode can take, and then let's see. And then I may place a fuse there actually. Okay. Like 600 watts. So this one is a pretty durable thingy. Unidirectional and bidirectional. Let's see. I'm gonna check if this is. I'm gonna check if this one is bidirectional. SMBJ48A. Yeah, so A is a unidirectional, which is good. So we got a unidirectional device there. And then we need to have a fuse that's 40 amps. Or maybe 50 amps or something like that. Could probably go up to 70 amps, but yeah. Let's go with 50 amp fuse. I mean, these fuses are usually very large, so they belong better on external connectors. Like, could have a fuse, like a screw-in fuse or something. But I'll see what I can find here. I think it's going to be like a 2 centimeter fuse or something like that. Let's see, fuses. There we go. Okay, great. So they have a lot of different fuses. We got 50 amps, like 400 fuses to choose from. Very good. So, I want to see if I can find anything with a connector. Surface mount. Bolt down fuse. So perhaps something for maxi fuse. Maybe, let's see. Yeah, they have fuse holders as a separate category there. Can we see something like maxi fuse here? Oh, this is, yeah. This is a lot to choose from. Type. Blade. Let's see. This is like 10 amps. Yeah. Anyway, I can green light this diode, D9, and I have to find some good fuse holder. Can I find something that okay, maybe something like automotive. Okay, this would be fuses. Can we find something that has some kind of generic shape? Something like this. Yeah, this is great. 30, 40 amps. Yeah. Maybe I can find something at Swedish Bildtema which I can use. Fifteen, 25, 30 amps. Okay. So this goes up to 30 amps. Okay. What is aircraft limiter? €155. Interesting. Only a few pictures. Okay. Blade terminal special purpose fuse. Maybe maybe I can choose everything besides surface mount. Possible? Yep. Let's apply this filter. Torpedo fuse. Transceivers. Okay, so this is nice. I have both the holders and the fuses. So this would be ceramic fuse cartridge. I don't want to have a cartridge. Yeah. Maybe cartridge fuse. And cylindrical fuse. Dummy fuse. No! Bug! Okay. Dummy midget fuse. Edison high voltage distribution, electronic automotive through. Okay. Fast acting ceramic tube fuse. Motor fuse link. Okay, this is so many things, so many categories to choose from. Maybe something like this. Okay. I think I'll go back a few categories actually. So more than half of them are not in stock, which is a lot. Let's see. So maybe I can find something here. Okay, let's go with a rating. So between 40 amps and upwards. And voltages 48 or more like, let's see, 58, 60 volt DC and upwards. So we're down to a more manageable number, 369 fuses. So I'm gonna get rid of all of these. Don't want to see them. Okay, this is better. Surface, why 15 amps? Why? Did I not choose anything that's above like 40 amps? Okay. Okay, so this is interesting. What is this? This is 900 amps. Okay. Let's sort this by price. Ideally, probably something like this. But this is surface mount, and this is, okay, this is 40 amps. Yeah. And I don't want to have something that's surface mount. I want something that's in a cartridge, because this fuse can go. This is not the type of fuse that we want to have to resolder. So maybe something like this, class G cartridge fuse. They definitely look okay. Industrial electric fuse, class G. Yeah, most probably something like this. But I just want to find the holder. Okay, so maybe we can look at E10. Let's look at the fuse holders. Okay, diameter 0.41 inches. It's like, that's like, what the? That's like half an inch. It's like 2 inches long. Whew. Okay. No. No, thank you. No, thank you. It's like 2 inches long. That's huge. They don't have to be that huge. Come on. Okay, now we are at the price levels where it becomes prohibitively expensive. Okay, so what about the glass fuse or the ceramic fuse? So this one is 6.3 millimeters, 50 amps. Okay. Yeah, cartridge fuse and then 6.3 millimeters in diameter. So we can find something here that's okay. So if we just set this to cartridge fuse holder. Yeah. So this is pretty much this is very very much what I had in mind. That you have one of these that where you just put the fuse outside of the board, and that is quite quite a good solution. But it would be nice to have something on the board to protect the TVS diode that we have there. Like, something tells me that this is this is not everything. What type of class is this? Fuses 6.3 times 32. Was this something? 6.3 times 32, right? 40 and 50 amps. 1. Okay. What type of fuse is this? SUT H. Maybe SUT H. SUT H. Does that mean class H? No? Maybe the datasheet says something. is no article number for any fuse holder. Okay, maybe Busman? We don't need to choose anything that's above. So I'm gonna farther restrict the current. So I want something that's between 40 and let's say between 40 and 60 amps. Actually 70 amps. Because 70 amps is the maximum current through the MOSFETs. But the connector is not designed to handle 70 amps, I think. $48.18. Okay, maybe surface mounted or something like, let's see, surface mounted. Square. No. Is there any fuse that I can easily just put on the board? Is there anything with a fuse holder? Yeah, okay. Right, so there is something like this. $5.20. Okay, these ones are not 520, but I think I'm looking for something similar. Maybe something like, let's see, 6.3. What if I look at the size? Okay, 6.3 millimeters, 1/4 of an inch. Six 0.3 times 32, yeah. Yeah, so maybe something like this. Let's check this one. So what would be the current? Okay, 30 amps max, which is not what I want. Okay, so probably something like this. Port number 01, 0109, yeah. Okay, it's probably H and Z. Let's see what the difference is. So that'd be 101. One oh nine, 129. 109, 129. So that's 13 of 60. That's quite large fuses. Okay. Okay, this is taking a bit too much time. I definitely need to think of a way to fuse this, but I have to find the right part. So I will stop this video now, and I'll come back to this subject a bit later.